Okay, all right, we'll continue. Okay, so today we'll continue our discussion with matrix inverses and do some hands-on work with the graph paper on inverses and their geometric meaning and stuff. Did you guys try finding the inverse using this method that we discussed yesterday? Put A here and then you put I here, and then if you convert this to I, this should come to inverse. Did you verify? It comes out, right? Okay, all right. Let's do one thing. We saw earlier. Oh, yeah. Yeah. So the graph, the graph paper is your R2. Maybe in the middle of the paper, if you draw the horizontal axis and the vertical axis, you can choose this as E1, this is E2, somewhere in the center. Okay, so there'll be this one box in your. So essentially, this now represents your 1, 0 vector. That's one of the basis vectors, and the other one is 0, 1, and that's your standard basis. Okay. Now, if I give you the vector 3 minus 1, okay, how do you draw it on that paper? Just draw it. Draw all this. We'll call this vector x. Make sure your origin is in the center. If you take the corner, then you won't be able to show when one of the components is negative. Okay. You have it? How did you get to that point? How did you draw? And I said 3 minus 1, right? How did you know where to put that point? Sorry? Uh, yeah, go ahead. Yes, yes. Okay. In linear algebra, you have to forget about x-axis, y-axis. I said 3, 1, and I said if the basis is not told to you, you simply assume it's the standard basis. The standard basis we've assumed is you've drawn that we've assumed that E1 is pointing in this direction. So this is your graph paper. What's happening today? Switch it off. Switching on. Okay. Yeah, it is going on. So, and then you chose the origin to be somewhere here. This was, you chose this as E1, E2. Okay. When I said 3 minus 1, right? Forget about the lines in the graph paper. All you need to know where this point is depends on where is your origin that you've chosen and what are the directions of your two bases, the standard basis vectors that you've chosen. So when I say 3 minus 1, that means the point that vector I'm talking about has 3 times of E1 and minus 1 times of E2. That means I take, this is 1 times of E1, 2 times of E1, this is 3 times of E1, and then I take minus 1 times E2, and the sum of these two vectors gives me this vector x. That is, if I add these two, I'm going to apply the parallelogram law of vectors. It means this is my vector x. Okay. You can call this the x-axis and the y-axis if you assume that the first basis vector, standard basis vector, represents the x-axis, the second basis vector represents the y-axis. But in linear algebra, we should try and get away from that language. We're now given a numerical value for a vector. The basis is not mentioned. That means it's assumed it's a standard basis. And if this is the direction for your standard basis, with this as the origin, this is the vector. But maybe one of you did not have the graph paper in the vertical position. You had it in the landscape position. Here, maybe you drew E1 and E2 like this. And for that person, this vector x would be here. Now, if you orient both of them the same way, right? Both of you would be talking about two different vectors for the same numerical representation. That is primarily because our choice of standard basis, I mean, both of us are using the standard basis, but the directions that we've chosen for what the standard, where the standard basis is pointing is different. So even if you're using the standard basis, if you have to know what vector these numbers actually represent, we still have to agree on, okay, we are using the same basis and that all of us agree on in what direction each of the basis vectors points. Okay? Here, because two people have used different orientations for the basis vectors. So for one person, it was like this. For the other person, it was actually E1 was like, well, here, and E2 was here. That is the reason why for this this person, this vector x came out to be like this. That means like this. They're not the same. That's because our bases were different. Okay? But if once we agree on the basis vectors and the directions in which they point, then both of us should essentially then have the same vector. Okay? All right. So when you were given 3 minus 1, the way you know what vector this person is talking about has nothing to do with the lines on the graph paper. Okay? It only has to do with where are my basis vectors, where are they pointing. I need to take 3 times my first basis vector, minus 1 times my second basis vector, add them together. That's the vector this person is talking about, or that's the vector these numbers represent. Okay. Now, so you've drawn the vector there, right? Okay. Now, and you can also verify it algebraically that x equals 3 times 1, 0 plus minus 1 times 0, 1, which means I'm taking 3 times E1 and adding minus 1 times E2. All of it adds up. Okay? Right. Now, in the same, let's say we don't like the basis, the standard basis. We want to work with another basis. I'm going to call it the A basis. Given by 2, 1. Okay. Now, I've given you numbers. I've not said anything about the basis. That means this is in the standard basis. Okay. Draw these two vectors on the same graph sheet. So you already have, you've drawn 3 minus 1. Let's draw two, A1 and A2. First of all, does this form a basis? I've confidently said A basis without checking whether the vectors I've chosen are linearly independent. Yes? Why? Sorry. That's what I'm asking. Why? We just talked about this yesterday, right? If you only have two vectors, by what? You cannot scale A1 and produce A2. That means they must be linearly. They're not collinear. That's all. Okay. Where would they be? So one would be like this. A1. Will be A2. Okay. You got it? Okay. Now the question is, I'm going to use a slightly different notation. I'm going to write it like this. XA, this means the representation of the vector X in the A basis. How do we find this out? Algebraically, let's talk about algebraically first. Tell me the procedure first. What is the procedure for finding out? We discussed this yesterday. Sorry? Gaussian elimination to do what? You use Gaussian elimination, I agree with you, but to do what? Gaussian elimination is used for solving a set of linear equations. What linear equations are we solving here? Can you tell me what that linear equation is? Yeah. It's okay if you're wrong. I'm sure you know. We just discussed this yesterday. Yeah, go ahead. Sorry? U1 is it? E1. See, what is the question? The question is, what is the representation of this vector X in the A basis, right? That means we are asking, there is some alpha 1 times A1 plus alpha 2 times A2. That gives me X, this vector, right? The question is, what is alpha 1 and alpha 2? Because your XA is simply alpha 1, alpha 2. And if you do this, get X, where A is the matrix with A1 and A2 as its columns. Okay, so the linear equation that we are solving, X is known, that's this vector. A is known because we know the two basis vectors A1 and A2. This is the unknown. That is the representation of X in the A basis. And the way you would solve this is by X, where we said yesterday that the inverse of a matrix essentially allows you to change basis. Okay, here X is in the standard basis. A inverse allows you to convert it and bring it out in the A basis after you do the multiplication. Right. Once you have this linear equation, then yes, you use Gaussian elimination to find the solution. Okay. Tell me what that solution is. What is XA? No? 2 by 3 and minus 5 by 3, is it? Did you verify it? How will you verify it? Sorry? Ye- Yes. Substitute for XA here and see if you multiply A with XA, you get X. I don't think it's correct. Or maybe it is. Maybe it is. Yes. Yeah, yeah, I think it's correct. It's fine. Okay, all right. Now, if we agree to only work in the A basis, right? And I give you a vector whose components are 2 by 3 and minus 5 by 3, how will you find out where that vector is? Okay, what do you do? This is all we have. Forget about the standard basis. Forget about the graph paper. The vector we are given is 2 by 3 minus 5 by 3. Now, how do we find out where that vector is? You don't have anything else. In fact, when you remove everything else. Yes, as I said, all we have are the basis vectors. Now, how will we find out? Yeah, what is it? You know, I'm sure you know. How do you do that? Sorry, I can't hear you really. Yeah, parallelogram law vectors, but what do you do? Fine, parallelogram is just adding two vectors, right? So what do you do with these two numbers and the basis? Okay, by how much? Okay, you can do that. Find out if you scale a1 by 2 by 3, where is that point? Mark it on your graph paper. 2 by 3 is what? Okay, all right. So you take 2/3, 2 by 3 times a1, that's somewhere here. Okay, and then what? What do you do next? Sorry? Yes, where does that come to? What is minus 5 by 3? Yeah, so draw this already. That will be 2 by 3 times a1. Where is now minus 5 by 3 times a2? Yeah, just draw it. Yeah, it'll be on the opposite side. Just draw the. You have a ruler. Just find out what is my 5 by 3 and then scale a2 by so much. Okay, notice that the 2 by 3 is 0.67. So you don't take 0.67. You don't take the ruler and then measure 0.67. It's 0.67 times a2 or a1. That means you have to find the length of a1 multiplied by 0.67, and that is exactly this point. Okay, so it depends on the length of your basis vector. Where is it? Am I here? Here? Is it okay? Or no? Okay, now what do we do? Okay, what is the next step? Sorry? Yes. How do you add now? How do you add two vectors? Sorry? Again, please be louder. I don't hear that well. So if you speak very in a low voice, I won't be able to hear what you're saying. Sorry? I get it. Okay. Are you saying parallelogram law of vectors? Okay, all right. So how do you apply that here? How do you use your scalar to do the parallelogram, draw the parallelogram? You're not sure? Well, place your rule. Place well. If you had a drafter, maybe it's easier. But place your ruler parallel to this line, and then simply move it till the ruler meets this point. So move it here so that the ruler is essentially stays parallel to this line, and then draw a line like this. Similarly, place the ruler here parallel to A1 and move it along A2 so that it stays parallel to A1 till the ruler comes here. That's your next line. That's your parallelogram. And this point where they meet, that is the sum of the two vectors. When you do that, where does that point end up? No, you're not sure. You have the two. What is it? 2, 1. 1 minus 1 is here. Here, this point. Those are the two vectors. That's your basis vector. Okay, draw it. Yeah. Yep. Hey, hold on. You've not drawn 2 by 3 times A1 and minus. No, why will it be there? You have it? Okay. Means what about the other side of the parallelogram? Yeah, just draw that one as well. Okay, tell me what is 2 by 3 length of A1? 5.5 by 3. Can you tell me these? Which one? That's root 10, right? That's the length of A1. Root 10 into 0.67. How much is that? Oh, if you've not calculated it, how are you drawing the point? 2 by 3 times A1? Okay. Yeah, okay. Okay, let's go through it step by step. We need to take 2 by 3 times A1. Okay. That's 2 by 3. So here I have a vector that is of this length. If I ask you what is half of this vector, where will that point be? Here. If it had length 10, where would you draw that point if you had a ruler? Okay, if let's say you did not have a ruler and I asked you, give me half of this vector. What will you do? What is the first step you'll do? Sorry? Correct. Total length. So the first thing you will do is measure what is the length of my vector. So do that. Take the ruler, or see, because you have, sorry, no, it's not root 10, it's 2 1, right? So it will be root 5. So yes, 1.4. Yeah. So the length of A1 is root 5. You're taking 2/3 of that. That's what? 1.4? 2 digits. 1.49? Okay. What about minus 5 by 3 times A2? What is the length of A2? Root 2. Okay. Root 2 times 5 by 3. What is that? 2.35? Okay, that's all. So now you take your ruler, and now that you've adjusted for the length of the vector also, now you simply have to go to, this is 1, 2, this is 1.5, that's 1.49. Of course, I've not drawn A1 to scale, but you know what I mean. That is your 2 by 3 times A1. Okay. Yeah. So this will be root 5. So you'll have to go 1.5 times at least somewhere here. So you go 1.49. So somewhere here. That is 2/3 of A1. Okay. That is 2/3 of A1. Where is A1 first of all? Hey, dude, A1 is 2 1, man. Okay. You have it? Okay. All right. Good. You almost got it. Okay. For minus 5 by 3 times A2, you take the scale. Give it parallel. So it has to be in the other direction. So take this as 0. So you have to go 2.35 units in the other direction. That is where minus 5 by 3 times A2 will be. Yeah, just draw it. It's fine. Oh, you don't have a ruler, is it? It's fine. Yeah, you're done? You're not sure? Sir, you're not sure about? So it's minus 5 by 3 times A2, right? Minus 5 by 3 is minus 1.67, I think, right? That means you have to go in the opposite direction, and the length of that vector will be, yes, the overall length of that vector will be 2.35. That means you have to move in this direction by 2.35 units, and that is where the second scaled version of the second basis vector will be. First thing I would do is I would draw a line, a light colored line. Actually, don't do that. Place it like this. And this line is essentially the subspace spanned by A2. You can get all vectors that are scaled versions of A2 if you simply just draw this. That's the subspace. But yeah, so you go 2.35. Yeah, about 2. That's where. Yeah, that will be your minus 5 by 3 times A2. Draw the vector. Right, that's 2 by 3 times. Hey, dude, it's minus 2.35, right? Minus 2.35. What is the direction of A2? Direction of A2 is in this direction. So if you say minus, you have to go in the opposite direction, right? Yes. Okay. All right. That's it. So that's okay. You got it? Yeah. So now these two are the vectors that you need to add, because this vector XA, where did I, this, no, I have to write it. The vector X is alpha 1 times A1 plus alpha 2 times A2. So if you add these two by doing the parallelogram law of vectors, you'll get some vector. Okay. So the way you add is, yeah. So often when you do this, right, it's a good idea to draw the subspace corresponding to each basis vector. Just draw that line. Yeah, something like that. I would in general just extend this line out, because we will need that later. So you essentially draw the subspace corresponding to A1 spanned by A1 and the subspace spanned by A2. That's essentially the line that passes through this vector and extends all the way to infinity. Yeah, that's it. That's all. Now, if you want to apply the parallelogram law of vectors, you essentially have to draw a parallelogram with these two as the sides. Well, this point, these two as the sides. So that should look something like this. Okay. Now, the way you draw that is you take this, okay, and then you very carefully move this so that it remains parallel, and then it meets this point. That's this. And then similarly, you do the other way around. Yeah. Okay. When you do that, what vector do you end up with on the graph paper? You done? That you yes, of course, because that's the representation. Yeah, because we started with 3 minus 1. Yeah. Okay. Does everybody have it? Okay. Okay. Yeah, that's all. So, yeah, that's all. Hey, are you sure? How did you get to this point? It's what is parallel? What is parallel to what? Here, this is what you do. Take this, okay, and then you move the scale, keeping it parallel to A1 until it meets the tip of minus 5 by 3 times A2, and then you draw a line like this. Okay, draw it. Yeah, this. That's one side of the parallelogram, or the third side of the parallelogram. And then you take this, and then you do the same thing till the scale meets this tip. Yes. Yeah. Yeah. Got it. Yeah. Great. Okay. What vector do we end up with? Yes. And that is what we were trying to solve. We are trying to solve a into xa equals 3 minus 1. Okay. Because the representation of this vector x in the standard basis was 3 minus 1. We used two basis vectors, A1 and A2, which were also represented in the standard basis. And then we asked, what is the representation of this vector x in the A basis? That's essentially 2 by 3, comma minus 5 by 3. And if you find out where that vector is in the A basis, you get the original vector x, because alpha 1, alpha 2 is the representation of x in the A basis. Okay, all right. Now, let's do something slightly different. Let's say we have a vector y That is again, I've not said anything about the basis, and I've not used any superscript. That means this is in the standard basis. Okay. Where is this vector? Draw this vector. You have it? Yeah, okay. 1 minus 2, 1, 2, 3. It should be here. Okay. Now, if I asked you what is YA, what would you do algebraically? Don't do it, but tell me what you will do. That means I want the representation of this vector. So I have the representation of this vector in the standard basis, which is minus 2, 3. Now I ask you, what is the representation of this vector in the A basis? That's YA. How would you find that out? Well, do this. You take Y and you multiply it by A inverse, and then you'll get YA. That's not what we're going to do. How will you find it out geometrically? From the graph paper. What would you do? Earlier, we found algebraically and then went to the graph paper. Now I'm asking you, let's do the graph paper first, and then, of course, verify it algebraically also. How would you find it out in the graph paper? Yeah? What do you do? How did you go from the algebra to the graph paper? You just have to reverse the process now. Yeah. What do you do? Yeah. Yeah. What is it? Yeah, it's okay. Sorry. Perpendicular to what? Okay, let's see. This was the A basis, A1, A2, and then the vector that you had now was 2, 3. That is Y, correct? This is what you have, right? Now the question is, how do you now find out the representation of Y in the A basis geometrically? There is some parallelogram involved, right? Okay, correct. What is the parallelogram? Which parallelogram? Well, we know A1 and A2, right? Geometrically, we know A1 and A2. What we don't know is how much do we have to scale A1 and A2. That is essentially the representation of the Vector y in the A basis. Length of what? Yeah, you can use the scale and find the length. Okay. You have the scale. You can measure the length. Okay, work in the opposite direction, right? Let's say you were given the representation of y in the A basis, which will be some beta 1 and beta 2. If you had those numbers, what will you do on the graph paper to get to y? Yeah. Yes. What will you? So you have beta 1 and beta 2. So what would you do? How much would you scale what? What would you use beta 1 for? Yeah. Intercept of what? Yes. With what? Correct. That's the first vector, right? What is first vector? I assume the first vector means A1. That's the first basis vector. Which point? 3.5. Yes. It is span of this point is somewhere equal to the. No. Wait, let me put it like this. If you knew that YA was gamma 1 and gamma 2, okay, what would you do geometrically? Sorry? You'll take the linear combination of A1 and A2, right? But how much of A1 and how much of A2? I mean, as we just saw it, right? XA was 2 by 3 and minus 5 by 3. How much of A1 and A2 did we take? This is alpha 1, alpha 2. We took alpha 1 times A1, alpha 2 times A2. So I ask you the same thing again. If YA was gamma 1, gamma 2, how much of A1 would you take and how much of A2 would you take? Yes. Okay. So now, okay. And then you would add them. Now the question is, how do you find the gamma 1 geometrically? Which distance? That we know, right? That is what? Root 5. Which vector? Okay. That distance also you can measure because you have the ruler. Yes. Eventually, this is what will happen. This is what is true. Your vector y will be gamma 1 times A1, gamma 2 times A2. That means this vector y has to be the diagonal of a parallelogram. But what parallelogram is the question? Because once you know that parallelogram, the length of the sides of the parallelogram will tell you what are, from that you should be able to figure out what is gamma 1 and gamma 2. Because that's what happened earlier, right? You had alpha 1, alpha 2. Your vector x was the diagonal of a parallelogram. And the side of the parallelogram were 1 times A1, alpha 2 times A2. You have to do the same thing here, except now earlier you had the sides of the parallelogram. Now you don't know the sides, you only know the diagonal. Now how do you find the sides? From A1, okay? Okay, all right. Yes, and do what? Correct. No, hold on. So you take your ruler, place it on A1, and then move it along A2 till it intersects with tip of Y. And then do what? What will you do after that? No, no. So you do, and then you take a scale off. You have to mark. You're going to mark something, right? Hey, hold on. People, what? You take the ruler, you slide it along A2, take it to the tip of Y, and then do what? Which point? A2, and that's correct. You have to then find the point at which the ruler intercepts A2. Yes, yeah, and mark the point. There you have it. Okay. So you place the ruler here. You move it along A2 till it meets this. So of course, draw this. Draw the subspace corresponding to span by A1 and A2. The ruler will intersect here. That's one. And then you take the ruler, place it along A2, move it along A1 till it intercepts, and then find where it intercepts. You place it. Sorry, I have not drawn it properly. I've not drawn it properly here. I'll have to look at your graph. Right. So you take this, move it here, you find this intercept. Okay. And the next thing, you take A2, and then move it here, and then find this intercept. Hold on, that's not where it is, right? Tip of Y is here. Have it? Yeah. Okay. Everybody's got it. Hold on, what is that? Here, you get the ruler. Y is the tip of Y is the diagonal, right? I mean, Y is the diagonal. So you have to go all the way up to Y, and then find where it intersects with not A2. The subspace span by A2. That means this line. Similarly, you keep the scale here, and then move it till the tip is at the tip of Y, and then find where it intersects with A1. Okay. Correct. So intercept here, and whatever is this intercept, the A1 axis, A1 subspace. No. So here, you found this out by doing this, right? Yeah. It will be here. It has to be parallel to A1. This is A1, right? Yeah. You move it, keep it parallel here. That's where here it intercepts here. Okay. Similarly, you go to A2 and move it along A1 till the scale is at the tip space. That means it will intercept somewhere there. Yes. So now this is your parallelogram, and the diagonal of that is Y. Okay, you got it? So the parallelogram would look like this, something like this, and this would be Y. Yeah? Okay. Now how do we find gamma 1 and gamma 2? How do we find gamma 1? How do we find gamma 2? Which point? So are you saying you measure this distance? Okay, all right. How much is that? Tell me. What is this distance? The distance along A1, or the distance along along A1. Hey, how did you get root from your scale? Use the ruler. No, use the ruler. Just measure it. It's 1. Are you sure? 14. Huh. What is it? இப்படி பண்ணியா 0.8. Okay, you tell me how much is it? 0.8 is it? Centimeters. 0.7. Okay, let's say 0.8 centimeters. What about the other one? 3.5. Okay. Now my question is now is gamma 1 0.8 and gamma 2 3.8? Sorry. That's 0.8 and 3.8 are not gamma 1 and gamma 2. 0.8 is gamma 1 times A1 or length of A1, and the 3.8 is gamma 2 times length of A2. That means to find gamma, you have to still divide these numbers by the length of the unit of your basis vectors. So this is not gamma 1, gamma 2. This divided by length of A1 will be your gamma 1. Length of A2 will be your gamma 2. Oh, yeah. Then tell me what is gamma 1 and gamma 2. Yes? Sure. Okay. Now let's just verify that gamma 1 times 2, 1 plus gamma 2 times minus 1, 1 approximately gives us minus 2, 3 or something like that. This should be approximately equal because our measurements are not super accurate. You could do this, or you could simply solve a times ya equals y. You'll get some solution for ya, and this should be approximately equal to 0.35 and 2.68. How much is it? Yep. 1.9 is it? Wow. Okay. All right. 3 point? There. Approximately equal. Okay. And in fact, if you solve for ya, you'll yeah, and then compare the solution that you obtain algebraically and geometrically, they'll of course match. Okay. All right. So we will stop here and then we'll continue this on Thursday. Sorry. Ah, yes. Yeah. I'm going to stop it.